Hi everyone, my name is Rahal and I'll be presenting our work caring about the human operator, haptic shared control for enhanced user comfort and robotic telemanipulation. Let's start with the motivation behind our work. Haptic shared control for teleoperation scenarios has been used a lot in the literature. It basically aims to share the control of the system between the user and the robot. It has been used, for example, to guide the user towards a desired position or trajectory, or away from undesired regions. However, none of these works focus on the user's comfort during teleoperation, even though this is a relevant issue in many applications requiring repetitive or long tasks. A few works exist on the topic in human-robot interaction, but not in teleoperation scenarios. Our main contribution in this paper is thus to present a haptic shared control method that minimizes the user workload during robotic teleoperation. We start by devising a new online metric that is based on the RULA estimation, commonly used in ergonomics to estimate the human upper body's effort. Using this metric and an inverse kinematics implementation of the human arm, we can estimate the user workload online. This workload is combined with the information we have about the task at hand to generate haptic active constraints that will guide the user to accomplish the task while minimizing the physical workload required. To calculate in real time the workload value, we assume that the user shoulder is fixed and that the wrist position is known from the pose of the master device. Using inverse kinematics, and without any external sensor, we calculate the arm angles, and the workload value W is basically the deviation from the resting pose of the arm. You can see in the pictures to the left, for example, a comfortable pose, and to the right, a less comfortable one with a higher value of W. Once we have this value, we can calculate at each instant the haptic feedback value, which is designed as the weighted sum of two terms, FW minimizing the workload, and FR minimizing a task-related cost function. This second term could be anything. It basically represents the task at hand. In our paper, we chose as a representative cost function the distance to the target in a pick-and-place task. The weights alpha and beta are of course designed and they depend on the application. To illustrate our algorithm, we show how the system behaves in a simple task of moving the robot from a point A to a point B with the same height. An alpha of 0 results in a straight line since it's the best way to minimize the distance between the 2 points. As alpha increases, the user is guided along a more curved path to improve the user comfort while teleoperating the robot. We performed a user study with 15 participants to test our system. The task consisted of moving the robot to perform a pick-and-place task on different objects and with different alpha weights. The results showed that an increase in the weight of the human-related component in the haptic feedback improved the user comfort by 30% as measured by the NASA TLX test results, at the expense of a slight decrease in the performance. As a summary, in this paper, we presented a haptic shared control method that accounts for the user comfort in robotic telemanipulation. We provide force feedback to the user that considers both human-centered and task-centered cost functions. More details are of course presented in the paper and in the video. Thank you for listening.